Okay, meeting in progress. Your board, you can please. So, how do I put the? So all the I go. Where do I go from here? And then I go. Okay, that's fine. And then I go into the materials, and everything's going to be there.
And you have it here. So now it shows.
Okay, but after that, I go back and all the material, and I click on the materials.
Yeah.
Okay, it's fine. That's what I thought, but I'm. Okay.
And then just wrap up your work. And then we do have a remote presentation, but honestly, the new stuff.
Okay, so I'll handle while you guys present. I'll handle the meter code. I'll do the meter code. It's fine.
Oh, and the blue sheets.
Yeah, blue sheets are here. And they usually have our name on it.
I'll still with that.
First, then 50. That's us. No, yeah, we need. There's more people than I thought. Okay, what time is it now? Okay. We're going to start in a few seconds. It's fine. Is Noah? Yeah, Noah's all right. Did she send her material? Yeah, okay. I have the slides from Noah. So while somebody talks, I'm going to upload them. Don't touch anything. It's under control. Okay. Everybody, could you please sit? We're going to start right now. There's going to be blue sheets going around. So please sign. So I hope that you know that you're at the proposed research group called Computing in the Network, and I welcome you to that. Okay, so it's how do we get out of here? Go.
Okay.
Thank you. Thank you so much. Okay, so again, welcome to the first actually official meeting of Computing in the Network. In Bangkok, we were a side meeting. In the meantime, we've been approved as a proposed research group. I'm the person in the middle, Marie-Josée Montpetit, with my co-chairs, Jeffrey Heath and Eve. And we have actually a fairly light agenda today, but intend to have a lot of discussions. So this is why we are going to have targeted presentations and just a few more, a lot of time for discussion. This is obviously the note well that we have to show, so everybody's aware of that, so I won't go too long. In terms of documents and locations, we actually have a wiki. Again, since last time, we also have an official mailing list, and there's 6 people who are currently remote participating on MeetEcho. Again, this is the agenda that was there before, so we want to talk a little bit about the current charter and some of the goals that we set for ourselves, and Yves has also some food for thought in terms of the work we've done since the last IRTF. We're going to have a presentation on industrial networks, which is one use case for Coin. Yves is also going to present something about edge data discovery. We have a paper that is actually a common paper that was presented at the ICNRG, interim meeting on Sunday, but is absolutely related to stuff that we want to do in naming. There's going to be also a presentation coming from the T2T RG in terms of what they do at the edge. And then we're going to have remotely Noah Zilberman, who's from Cambridge University, who has these great ideas about what computing and a network can become. And then we want to open the discussion. We just have a few slides to make sure that you discuss. And then we'll stop. And we have 3 ideas right now. One from Jeffrey on managed networks that is evolving. I started writing something on extended reality, which uses a lot of edge, a lot of computing, and a lot of naming. And obviously, there's a draft from Yves and her collaborators on edge discovery. We obviously want more, and we hope that the discussions of today and the presentations of today will spur your enthusiasm to submit more documents and make this even more successful. We are going to also start using the list much more to encourage discussion, so you may see traffic there, and we hope that you don't spam us. So.
Okay, so good morning. So the most general goal of our COIN research, proposed research group is to foster research in computing network to improve the performance of the network and the efficiency and also user experience by thinking the compute, storage, and the network in a holistic way instead of separately. So main focus will be the use cases from real world and also the work in progress from different communities, and then explore the architecture and of course potentially protocols. So we have modified the charter after the Bangkok meeting based on the discussion in mailing list. So thanks to Dave, Dirk, Laurent, and all the contributors. So for the details of the charter in our wiki, and the main objectives is to systematically look at different instantiation of COIN in the computer continuum. So Eve will introduce a little bit more about this. So we will explore where there are common principles, abstractions, and then architectures, etc. And also what's the impact of such kind of in-network computing on the traditional transport and the security, because it's the packet goes through this in-network computing and not necessarily intact, right? So what's the impact to the reliability and the context control? So this could be something interesting, and also others. Thank you.
Okay. I think I'm going to present from below.
Okay. All our pictures disappeared.
Oops, all of our pictures disappeared. We're not exactly sure why.
This was supposed to be the matrix, by the way.
Oh, basically, on the mailing list, if you've been participating so far, we had some dialogue around the charter and our objectives, and what we all tended to agree on, even though we come from various disciplines, some securely grounded in the data center, others very much at the bleeding edge of edge computing, was that there's this continuum that we shouldn't really be thinking of them as separate places for conducting compute in the network. And so we were calling it the continuum, and therefore we were thinking of time-space continuum, we were thinking of the matrix. So that's, as you can see, there's a beautiful picture of the matrix here. Choose the PDF version of it. Okay, I think I'm going to present from down below. I think it'll be a little easier.
Okay, hold on. Well, you reload.
Does this work? Are you reloading? Okay. Okay.
No. I'm looking for that.
We don't need our pictures. I think we should just present anyway. Let me see if the clicker works. Oh yeah, there you go. Yay! Yeah, let's go back to the matrix. Okay, there you go, picture of the matrix. So we'll be speaking a lot about the continuum because we think that maybe a systematic way to frame this discussion is about talking about the various places where coin will reside in that continuum. I think I may need your help here. As you can see, we're newbies operating the technology.
Oh, it's just I'm newbie with this computer. Before you come.
Next time, we'll know the technology. Da-da-da-da. Okay, it's sort of working.
Okay, good.
All right, so what does the continuum actually really mean? In the beginning, when people talk about edge computing, they'd say there's a back-end data center, there's on-prem or closer to the edges of the network, data centers, and that was the framing of the discussion, that edge computing was data centers, but just closer, more proximate to where the action's happening, where the data's getting created, where it's getting processed, and ultimately where the decisions are being made and maybe even actuation happening. But if you watch what's happening now, one, there's this proliferation of edges, not just at the edge, and many providers providing edge computing, but the definition of the edge is fairly ambiguous because depending on who you are, these edges may be the telco edge, it may be the enterprise edge, it may be the game console edge, etc. So there's this proliferation of edges, and some of these edges are happening in very managed networks, and others are more in the wild. If you think about smart cities and such, it's really about the federation of resources that are proximate. And if you follow the arc of this discussion, that in the extreme, everything becomes an edge, or depending on your perspective, if glass is half full versus empty, all of the things become data centers. So it's really a reimagining of the data center. And so the conversation about edges is really a stepping stone to beyond edge computing. There have been some sessions on that here at the IETF, fog computing or ambient computing. There's also proliferation of names given to this area. So now that we've established that there are other kinds of edges, not every edge is going to provide the functionality that you might find, all of the functionality that you might find in a data center, by which I mean compute, network storage, as well as control, data management, and so forth, and that now we've got little pieces of the data center scattered about, so there's really a disaggregation happening as well regarding the data center with regards to its services, the service offerings. Now, we bring this up because really depending on where this compute gets placed in this continuum, the kinds of compute that typically takes place is going to look categorically different. And so in data centers, and some of the presentations that we had at the last meeting at the BOF, focused on consensus algorithms or algorithms focused on the key value store problem. If you talk about compute at network switches, firewalls, or routers, you're really talking about packet inspection and acceleration of packet header functionality, crypto. Now, as you get into the IoT and RSUs, which are roadside units, there's lots of discussion about the interaction with connected or autonomous cars or vehicles. And so some of those algorithms are about high definition maps, the splitting of the processing and the updates to models and so forth, as well as the stitching together of videos. We had a presentation last time about the ubiquitous witness, which was about the upstream flow of data. And then finally, smart cameras. And that there's obviously a lot of work on compute being about the analytics of object recognition and the labeling of video streams in flight. And in addition to the fact that location influences the kind of compute that's happening, some of that compute, as I mentioned, is going to be more managed than others, or at least the devices on which the compute is happening is going to be more managed. Now, the implications of this continuum is that we have to ask what's the sort of form factors of these elements in the network? What are these boxes doing? What kinds of infrastructure? And what's also quite interesting right now is where the stationary infrastructure meets up with the mobile infrastructure. And so this kind of conversation about computing the network is happening at all of those places. And so a lot of the discussion is around, at least in the standards community, is around racks of servers in what you could call these data centers our central offices, and all the different places that get further and further into the core network and then at the back-end data center or warehouse-sized data center. But we could also be talking about putting the compute on base stations and access points. But then we also have to consider in the extreme that the other places for this compute could be at the devices themselves. And really one of the discussions we'd like to have today is about should the devices be part of the continuum from the cloud to the edge and then to the device. And so some of the devices are things like cars and phones, drones, robots, and head-mounted displays, which may not always be connected to a back-end infrastructure. Lots of other questions. I won't go into all the details, but just to get you thinking for the discussion is where in the architectural stack, whether in hardware, firmware, or software, should this compute reside? Because we tend to, as a community here at the IETF at least, talk about network boxes and that the compute is about network functionality. And as Jeffrey alluded to, that for truly improved performance of compute in the network, we really need to also consider a partnership with storage. And finally, there's a discussion that we don't talk enough about, which is what's the consequence to the user and as well as the developer? Just because we want to have these delineations between data centers and edge computing and everything in between, developers aren't going to want to have to comprehend some number of different API or toolkits, SDKs, in order to program those frameworks. So they just want to have their jobs placed in the most adequate, efficient place, actually. And we want to probably provide some guarantees that what we promised in terms of compute in the network was actually met. And with this abundance of data that comes with so many things connecting at the edges of the network, that some of that compute is going to be about aggregation to reduce, to try to fit within the resources that live in these aggregation or collector points. and that we're going to need to manage some of the implosion of the data. So without further ado, I hope that will get you thinking about the kinds of questions that we have. I will hand this over to Marie-José.
Okay, so because there's only one slide here, I will. You can actually ask a question now if you want, but as you wish. We also have like the whole rest of the, after the presentations, we reserved a whole bunch of time for questions and discussions. But if you have a question now, go for it.
Yeah. Sure, let's talk about scoping later.
Okay, so we will now have the presentations, and we decided that we were also going to put questions in your mind before we start the presentation. So we expect that there are going to be discussions and questions about, what are the goals of today's presentations. So obviously we want to explore the coin continuum and the state of the art. We want to define the potential topics and some of the stuff we would like the research group to look at. We want to identify, obviously, what else is needed. There's a few people have been strong contributors. I see a bunch of very new faces here. So there's probably ideas that none of us has had before. So we want to do opinions about what we should be doing and what we are, and identify also, obviously, drafts and contributions. So now it's Boris. Okay, so now you have to tell me how I should go through this.
No, I'm not sure. I have to share my presentation.
Hold on. Yeah, okay. It's fine. He's presenting. So.
This presentation has a lot of PowerPoint.
But I guess, okay, that's good. We're good.
So I need to run it from this laptop. Okay, my name is Börje Joman for Ericsson. This presentation, as Marie-José said, was given in the ICNRG. Then it was given by Unur Askil from University College of London. He has left, and so when Marie asked to have it presented today, I offered to do that. The basic back idea in this is from an idea on keyword based naming for ICN IoT domains that was presented in this paper by these people at the ACM conference in 2017. So ICN basically offers the idea that you ask the network to get the piece of name data. You don't request it from a certain place in the network. You just ask the network, get me this data, and then it delivers. It also have the idea that when a router forwards a piece of data, it caches it in case somebody else would request it soon. If we then add processing out to this, ICN can also help finding functions in the network. If you name the functions, it will find the closest nearby function where processing can be done. Why we need edge computing, I guess I don't have to explain here. So what we are proposing here is a store, process, deliver service for the edges of the network. So you first find the data by name, and then find a function if needed, and then you deliver the data to a destination. So yeah, that's what we're doing. So we find the data, process, and also store the results in case somebody would need make the same request within a certain time frame. So basic example, we have devices that stores data in caches in the edge of the network. And then somebody is interested in some information and sends a request into the network. It includes a processing request. It finds somewhere where it can be processed. Then the data is located and it's brought to this location and processed. And finally, the result is delivered back to where it was requested from. It's also cached in this node where it was processed. So you can find it if somebody makes the same request. You don't have to go through the whole process again. So what we are investigating here is how is a good naming for this. And I should say this is not a final developed naming scheme or anything like this. We are investigating this in a project called ICANN 2020. It's a EU-Japan collaboration project where we are working on this. But these slides are intended at to be some ideas on how this can be done. So existing approaches includes having hierarchical naming. This is, for example, used in ICANN approaches as CCN and DN. There is this tag-based naming proposed in the paper mentioned. And there is a RFC who explains how you can use hash-based naming in a structured way. It's coming from another ICANN approach, NetInfo originally. So the proposal here now is to combine this tag-based and NI naming. And what we would have then is that we have an authority part, or you can also think of this as a publisher. Someone is publishing some information under a name. So this authority can be used also to route to the domain where the data is published. You have a digest that is the name of the data that can be used for caching. And then we have the function name if there is one needed, and then you have a number of keywords or tags or what you want to call it that is used to identify the data that should be used. So if we first look at the authority part here, that could, for example, be a CCN name. If you have a network where you route by name in the global network, you could also have a DNS name, use DNS to do a lookup, get an IP address and route to the IoT domain by an IP network. Then the digest part is used to give a globally unique name to what you're requesting, to the result, so you can find it in caches. In the future, it could be, if you have a processing function with a set of data, this name could be the hash of the function and the set of data. So if you get the same question again, you can just look up that result. And function name is obviously the name. Oh, sorry. Oh, there isn't a slide on function name because it's obviously the name of the function. So then for the keywords, one of the reasons they got into this idea is that it turns out that to structure data like sensors in the building and on floors and so on in a hierarchical way is not always easy because different applications have different ideas. Somebody's more interested in having it focusing on buildings, other on all the floors and so on. So it's soon becomes awkward to have strictly hierarchical names. With this keyword thing, you can just give a set of attributes that the data should match, and those data that matches that set of attributes is what is returned. But this, of course, doesn't scale globally, but in a local IoT domain, the claim is that this would scale. So concrete example from UCL campus computer science, you have the hierarchical part, then you want the maximal temperature in the foyer. Could look something like this. Yeah, I don't get into the RISE protocol here. This is more for the ICN people.
About 2 to 3 minutes now.
Yeah, I think this is the last slide, so this is fine. So what are the advantages with this keyword thing? Yeah, I think I basically already said this, that you can find it without having to have a strict hierarchy, and you find the data and you process it. And then we also have the possibility here to reuse results as the results is cached in the network. So if somebody make the same request again, you can just deliver the result instantaneously.
Okay. Thank you. Any questions? Okay. Thank you very much, Gloria. I know it's hard to step in presenting other people's material. The next presentation is on the industrial networks use case. No, he's presenting also. Well, hello. Yeah, I have a connector.
Sorry?
If you want to use the clicker.
I have a clicker.
Okay.
Okay, so my name is Klaus. I'm from Aachen University, and I was asked by Jeffrey to talk about our ongoing research in the area of industrial networking and computing in the network in industrial networks. So this is, I guess, not a typical ITF talk, and I haven't followed the work of this group so far, so maybe there's a bit redundancy here. Okay, so if you take a look at an industrial setting, like what you call nowadays typically Industry 4.0, you expect something like this. So a lot of robots doing smart manufacturing. Then, of course, since it's smart manufacturing, people think this is all connected. But there's one component missing where all the smartness actually is executed. So there are edge cloud and remote clouds and so forth. Typically for us, we see three use cases when we think of industrial networking and in-network processing in this area. The first one is network control. So controlling the operation of the robots, controlling the operation of the machines with all the control loops and so forth. This is not done anymore locally in the machine or in some PLCs. This shall be done in edge clouds, or people even think about remote clouds. A second use case is collect all process data and analyze it. So as I will show later, from such a production process, you can actually pull a lot of interesting data on the production out, analyze it, and then improve the manufacturing, learn about it, and so forth. Sometimes you also want to have immediate feedback. For example, if robots shall cooperate with humans in the same area, then you want to have some safety measures there. And the last thing is offline data analysis. So if you collected all that data, then you do long-term analysis, data mining, machine learning, and all that things in order to find interesting things out. Okay, so let's dive a bit deeper in these three use cases here. So the first one are network control loops. So the setting looks like this. You have on the one side the sensors and the actuators. So this is actually the robot, the input and the output in the robot. And then you have the network, which transports all the data to the edge cloud where the control algorithm shall work in software such that it can easily be adapted, changed, and so forth, because in these settings, production is not meant to produce hundreds, thousands, or millions of pieces, but to change the production process even in real time. Okay, if you take a look at this, you actually have this communication loop here. And the latency for these things is quite high. Even if you have an on-premise edge cloud, the latency for certain control loops, for robot control and so forth, is in the areas of 2-digit milliseconds, and that's too high for real-time critical processes. So our suggestion here and what we are working on in our research projects at the moment is that we use in-network processing in order to push a lot of intelligence or a lot of control functions from the control algorithms into the switches and process them in programmable switches, for example, with P4 or other means. And that drastically reduces the latency, and then you can support these processes. Typically, I compare this with the analogy of the human body, where you have the brain who does the main control of all the actuators. But if you touch a hot surface, it's not the brain deciding to take the hand back, because that would be too slow. It's a reflex that is actually done in the nerve system, and that's why we call this approach also reflexes, but it's basically an in-network processing approach. I have a simple example here, an academic example. Typical control people use inverted pendulums in order to show the effectiveness and the quality of control processes. And you see here an inverted pendulum where you can control the carriage, and you try to stabilize, you try to move the carriage in a way that the pendulum is stabilized. And in this case, the latency is too high. I think in this example, it was something like 20 to 30 milliseconds, and the control algorithm was running in an edge cloud. And depending on the length of the stick, it's not able to stabilize the process. What we then do is we derive a simple version of the control algorithm, push it into a programmable switch, and then, of course, reduce the latency of the reaction tremendously. And you see it's actually running here. So the inverted pendulum can easily and stably balanced. Okay, but this is an academic example. Real production examples here are, and these are examples that where we are working on, for example, here, an arc welding, welding robot, which is, it's not working now, but you can see a robot who uses a light arc to weld pieces together. And here we have control loops where we require latency in the single-digit millisecond area. And the interesting things here are the input or the sensors that we have. These are HD cameras, infrared cameras, and, for example, the current that is drawn by the light arc to produce the light arc, how much current it uses, and then controlled will be the robot positioning and the voltage of the light arc. And here you really need immediate feedback in the millisecond area. And here we, if we would use edge clouds, which are not exactly next to the process, which is typically the case on the shop floor, then we want to use in-network processing in order to do the basic calculations and the basic control in the network. The second example are cooperating robots, where two robots try to do things together, or you have human-robot cooperation, and there you have similar requirements. You have tons of sensors there which are networked. Each sensor is connected to a different network. A lot of wireless networks are in the game here. And here we also try to achieve the latency requirements by doing simple computation tasks in the network. Also, in such cases, typically when humans are involved, you want to have augmented and virtual reality in order to cooperate with the robot. The special case here is the human-in-the-loop detection. So you try to define safety zones. If a human enters the agility range of a robot, then you want to shut it down, and therefore standardizing that and get it certified, you need to ensure certain minimum amounts of latency.
2 minutes.
Okay. Another use case is the collection of the process data. So if you try to analyze your production, you can actually gather a lot of data and push that into a cloud where it's then analyzed with machine learning and other data analysis techniques. But this data is a huge amount. So this is just a simple machine, just one piece of a whole production chain. And you can see below that there are several sensors with megabits or even hundreds of megabits per second data producing, which needs to be transported through the shop floor and stored in the cloud. So our approach here is also that we apply filters, reduction filters, compression filters, aggregation filters, pre-processing and so forth in the network in order to reduce the amount and then enable the gathering of the data and then the later on processing. Okay, so our proposed framework in this area is that we want to use in-network processing to do simple tasks in the network, to do network control, to do reduction and pre-processing of data, and to have still the main control in the cloud, but that is then the latency in variant or the not latency critical part, which is then done in the cloud. What we see as a link to IETF here is, or why we want to contribute then from now on to this working group, is that we want to raise the discussion about the computational capabilities, what should be in these switches. So for our use cases, a bit more math would be nice, but just simple math and must not be, or simple computations are okay, must not be Turing complete, but execution at line rate, or at least with predictable execution times would be cool. And then we are working on the whole configuration monitoring management issue, so making the open flow version for pushing computation into the network to do simple tasks. And of course, we want to discuss transport protocol issues like it's a breaking of the end-to-end principle, and how do you deal with encrypted data, because also on shop floors, stuff will be encrypted in the future. Yeah, that's basically my...
When you review your slides, we're actually not a working group and we're not the IETF, so please put IRTF and
yeah,
research
the last
group.
time I was here, it was 10 years ago, so...
yeah, we probably didn't exist. Are there any questions? Thank you for this presentation.
Yes, I'm Dirk Kutscher, Institute of Emden in Germany. So this is really nice, so thank you for this motivation. Just one little comment. So I think one of the really important motivation for doing this is that if you think about these control systems, it's not only about latency, but quite often about deterministic communication.
Definitely.
But that is just emphasizing the need to do something in the network because, well, you have two options. You can extend the deterministic networking like to the cloud, which is super costly, or you could do something along the lines that you described, which seems to be attractive. I had one question. So you talked a bit about possible implementations. So you mentioned P4 and so on. What is your assumption about, say, the protocols and maybe the security abstractions that would be used? Do you think this is a, say, controlled domain that is basically kept apart from, say, the rest of the network, that you basically don't need to care so much about security? What is the assumption here?
So if you discuss with companies or production companies or mechanical engineers, they actually do not really care about security on their own premise. But as soon as any data leaves their premise, they are completely cautious, careful, and so forth. If I would engineer such protocols, I definitely would count security or would consider security from the beginning. if I take a look at the plethora of protocols that are used in such areas, it's a mess. So actually that should be that would be a nice playground for IETF to actually dive into industrial networks, and because they actually want to use IP because they think it's a cool thing, I guess. They do not really understand what it means. A lot of use cases we investigated use TCP for latency critical control traffic. That's ridiculous for us. Definitely, I would consider security as an important issue, and especially if you want to do in-network processing, then the thing with the encrypted data is how do you deal with that? We have several ideas. I'm happy to bring them here into the non-working group, but the discussion group.
Well, you should post your ideas on the list and generate discussion about this. That would be fantastic.
Yeah, but I definitely would agree that we have to consider security here and define secure protocols here.
Yeah, right. So what I wanted to point at is that if you basically have to take this into consideration, then this may have some impact on the tools that you actually use. For example, if you think about P4 programming, often there's the assumption that, well, you can intercept packets and flows and do some computation on those, which would probably not work with many end-to-end security protocols.
But that's what I mean with defining protocols for these use cases. For example, you can say we have only a part of the data that is computed in the network, and that we may deal with option headers or other things. So we define an option header for in-network processing or something like that, where the main part of the packet is encrypted and only that part that will be used by the switch to be processed in the network is either not encrypted or it's encrypted in a way that the switch can decrypt it. Yeah.
Thank you.
Yeah.
Thank you. Very interesting. Philip Eardley, so just on this end-to-end bit, can you explain where the end-to-end principle's being broken? I mean, I'm imagining you kind of got in your industrial network, you've got a sensor and your robot, and aren't they the ends?
Usually when I teach my students about the end-to-end principle, it means that packets are not touched in the network except for routing and changing those things that are defined. And if you have transparent elements in the network that sneak into the packet, you can discuss if that is a breaking, but if you actively manipulate a packet in the network, that is for me a breaking of the end-to-end principle.
Yeah, sure. But I mean, I'm trying to go imagine back to your example you had with your robot and things. Yeah. So on the two robots, the two ends of the thing, where is the in-network
I forgot something in my
done?
figure. I can show that.
And after the last person, we'll cut the line before the time. So there's 3 more questions after you. That's
so
fine.
Basically what you mean here is, so if you have this processing in the switch and the direct answer is going back to the robot, in our use cases, still the data is going to the cloud to be analyzed there. So this is, it's not shown correctly here. So the actual transport is still going to the edge cloud, but there's a short answer by the switch. And that is for me then a breaking of the end-to-end principle, because there is a reaction on the packet which actually should come from the edge cloud because it's the endpoint of the communication, but it's done before.
So Dave Oran, Network Systems Research Institute. 3 sort of tightly related questions. Yes. One is that it seems like DetNet-like quasi-synchronous communication is important in this environment. And even if your process is not Turing complete, it is in fact not necessarily synchronous when you hand something to P4 code. Does that mean that any program that's running in the switch actually has to be included in the scheduling algorithms for the underlying network? That's question number 1. Question number 2, how do you maintain the synchronous clocking that's assumed? And question number 3, have you thought at all about program composition in P4? Because you're not going to have one program running all the time and have to reboot the switch, if the production line changes what it's doing. So they're all sort of tied up together with that model. Oh, there was a 4th question, which is the model here seems to be you do data transformation in the switch, but you neither increase nor decrease the amount of data flowing. In other words, you're not consuming a bunch of packets, doing some computation and generating new packets. It just seems your only thing about computation is that modify data, read and modify data in packets as it flies by. So they're all sort of tied up together.
I hope I remember the 4 questions. The first 2 I can answer yes. I do not assume always synchronous communication here. So all the work we do with control theorists is that we actually do not require synchronous communication, but these control algorithms are able to adapt to varying latencies. But they say the lower the better. The last question, I think there you are mixing up a bit the use cases I showed. So for this use case, of course, we do not reduce the network traffic, but in this case, we do not have a lot of network traffic. Just a second. In this case, we actually have a lot of network traffic, which we try to reduce by filtering, by categorizing, and so forth, by reducing the precision. So here we really can reduce the amount of traffic that is produced tremendously. We have a paper on that. It's mentioned on the slide before. Yeah. Yeah. That this is not real-time critical here. This is about bandwidth. This is not about real-timeness here. But that machine I showed you that can produce up to 6.6 gigabit of traffic. Just one machine. That's a lot. We can reduce that significantly. Yeah.
Okay, Will Liu. I don't have so many questions, so I just have one clarified question. So on your last slides, I noticed that you mentioned about, a possible architecture example about this interface, northbound, southbound.
Yeah.
And I'm curious because I participated the last year's site meeting. So from what you wrote here, do you mean that there will be a kind of a southbound interface, a sort of standardized southbound interface between this computing function and the switches?
Not between the computing function and the switches, but between the, my basic assumption is we have some main algorithm, some main task in the cloud, but if it is executed in the cloud, it doesn't fulfill the latency requirements for certain use cases, as the first one that I showed. Then we push simple computation tasks, which we derive from this algorithm, into the switch, like filtering, like fast reactions, and so forth. And the northbound, southbound interface is rather meant between that, so between the cloud and the switch. So how do I push simple computation tasks into the network? How do I control that? How do I manage that? How do I deal with state? For example, if the robot is moving, then I have to move state to another switch, and then it's executed there, and so forth. So these are interesting questions which I address with this configuration architecture here, or with this interface here. Yeah.
Hello. Hello, thanks for the presentation. I'm Emil from Orange. I have a clarification question about the second bullet. Is Turing complete a feature or
if we could get it, it would be nice, but it's not recommended. So maybe I can talk a second about how we started with this. So we started with simple eBPF programs in the Linux kernel. And if you want to download or if you want to load a simple eBPF program to the Linux kernel, it has to be passed through the verifier. And the verifier limits it to 4,000 instructions, no loops, and no other things. Since we are also working in program analysis for protocols, we actually said we can easily guarantee that a program can have loops but will not run infinitely. So typically, when you give somebody the ability to run code somewhere, you are afraid of it can run in an infinite loop, it can have bugs, and so forth. And I guess operators are afraid if you would have the chance to download something that they'll download some code to their switches, which brings them into infinite loops and other things. And therefore, typically, they either restrict the effectiveness or the capabilities of these execution environments by not allowing loops, by limiting the number of instructions they can execute, or by having tools which actually can guarantee that such cases cannot happen. I'm more a friend of the second version, but yeah, that depends. But of course, to have Turing-complete execution environments would be nice, but I think operators have a different opinion on that.
Thank you.
Yeah.
Thank you.
Okay, thank you very much for your presentation.
Okay.
Is Matthias here? You know, I have your slide. There we go. And you have the clicker? Okay, good.
Hello, I'm Matthias Kovac with Huawei, and this is at best a teaser of what we are doing in the Think2Think research group about Edge and IoT. The main goal is to discuss with this group how these two research groups basically should or could work together. So a quick refresher what we have done. So the topic about edge computing and how it's relevant for IoT was first discussed at the IETF 98 in Chicago. And Dirk actually presented the compiled results from that here in Prague in the other room up there. We then had some more topics in Singapore where, for instance, Dirk and also Yves worked on the survey and the gap analysis for the topic of Edge and IoT. And we also had some visitors from the Beyond Edge Computing mailing list to present their problem statement. And actually last time in Bangkok, also the Think2Think research group people joined the COIN meeting to see what is going on in this activity and how does it relate. And we discussed in a pre-meeting, so basically last Friday, where we should go with the topic about Edge and IoT in the Think2Think research group. We had some questions. So one of the classic ones that you probably also had is Think2Think research group the right research group to do this work? The gap analysis and so on showed already that it's probably a good place for the distributed and lightweight aspects of the challenges that are discussed in edge computing. And we also confirmed basically last Friday that it's a good place to look at it from a device-centric view. So for an IoT device, what would be the next hop? It's probably something that is close to it, so meaning in the edge. And we also discussed if we have actually enough interested people, so enough workforce to work on this topic. And it showed that there was actually a quite good number of people, so we have the critical mass. And maybe interesting was that in particular for industrial applications, there was quite some interest. And then one of the main questions, so how does this relate to Coinrg? Since you touch similar topics, it became very apparent with the previous presentation that this is something that on a overview we basically have in common. So what we thought about, maybe we have to move some of the topics here. However, we found that there are enough people with interest to work on this in T2TRG, but maybe providing exactly this thing-centric view might be a good contribution to also help defining the challenges and also think about the solutions here in this research group or proposed research group. Another question I would have is where are the people from the Beyond Edge Computing mailing list? So I saw that there was not that much traffic. Are those people basically now here? Would there be people working a bit more on the tangible problems, let's say, of IoT devices so that we could motivate them to join us in Think2Think research group? That's something we could discuss later. To give you an example, what we are discussing and how we are approaching the problem. So one example is that it's kind of clear that many of the IoT devices require some supporting services because they are constrained in their nature. So this could be compute, could be something like a simple unit conversion of some of the numbers that you receive. It could be a format conversion, but it could also be like heavyweight tasks like semantic reasoning to adapt to a certain environment. Storage is quite interesting. IoT devices produce a lot of data, so where should they offload them without being necessarily tied to a specific cloud to send all the data there? And the question there is, of course, how do these things find the right service that is responsible for them or fulfills the requirements? The quite interesting question is, what are these natural compute nodes actually for IoT applications? So for configuration purpose, the smartphone, for instance, became the go-to device and is now used in many of the applications. But what is basically the compute or storage equivalent that you would find in these environments? And this, of course, heavily depends on the application domain. So it's different in the home than from a shop floor, for instance. For this reason, we want to split up the work also in the different domains and basically figure out what are the differences. Overall, the approach, how we do it, how we figure it out is probably similar in the different domains, but we have to collect the use cases, which are definitely different. As I mentioned already, there's a high interest in the industrial topics to work on this, but we also have consumer or the home environment as kind of our natural turf because we always use these light bulbs to illustrate the problems of IoT. Last point was if virtualization is something that should be in scope for the Thing-to-Thing research group. There are some technologies like unikernels, so a very lightweight virtualization approach that could work for some of the smaller devices. So virtualization itself is not a topic for the IRTF or the IETF itself, but we have some problems that could be interesting. For instance, bindings or the orchestration logic has to live somewhere, so you have to deploy it somewhere, and these aspects of the application are independent from the life cycle of the devices or the things themselves. So we need some kind of deployment mechanisms for this, and problems in scope are the interfaces. So how can I deploy a certain orchestration logic? What would be the right node? And then probably also some consensus among things to really elect the one that should be in charge of controlling certain devices.
Can you conclude your overtime? Oh, okay, cool.
So the next steps are basically, is there the interest to set up some kind of more formal liaison so that we have a common picture how to work on this. One question is, how should we coordinate this? So should we distribute questions beforehand? Should we just exchange some results that we came up with? And quite interesting would be if you maybe already have some concrete work items, some ideas that might be a better approach from a thing-centric view, for instance, and how to continue.
Thank you very much. For the sake of time, I'd like to push the questions to the list because obviously these questions, I'm sorry, Dirk, these questions, are basically questions for both the Thing-to-Thing mailing list and our mailing list. So I would push that there and see what happens and see how we can coordinate. And I think there is a way. Thank you very much for this.
Thank you.
Noah, online. I will load your slides.
Thank you.
So now we have a presentation from Noah Zilberman, who is at Cambridge University. Oh, come on, her slides not there. They're on. Reload, yes. Reload. I hate that computer. Not there. I loaded them. Give me 1 second, I'll reload them. I tried to reload the page. Okay, hold on. Oh, there we go. Okay, thank you guys. Okay, we can start.
Okay, thank you. I'm going to talk. Sorry.
We hear you, but
okay. So today I'm going to talk a bit about the vision of computing service providers This is based on our work in network computing for the last several years. And you will see throughout the presentation also some links to published work that we've done in this area. If you can please click. Okay. Thanks. Okay. So if we are looking at the amount of data that has been going through the network in the last few years, and on the forecast, you all know that we are already talking about zettabytes per year, and about tripling the amount of data that is supposed to go through the network within 5 years. Now, once we start thinking about what it means to our communication infrastructure and being able to continue and scale with this increasing amount of data, as well as what it means in terms of processing. Now, we already know that computer architecture has reached a wall in terms of the end of Moore's law, but still over the last 10 years, the improvement of in performance of servers has improved 27-fold. But when you look on the increased performance of networking devices over the same amount of time, it has increased 200-fold. So we have an increasing gap in performance between network devices and CPUs, and it's already an order of magnitude. If you can please move to the next slide. And the reason for this gap is the way that the architecture of these devices is implemented. CPUs basically move instructions through the pipeline. We are talking about a pipeline that is 64-bit wide, and all the data resides in the memory. In contrast, if you are looking on switches, in switches we have data moving through the pipeline, where the instructions basically reside in the memory. These are the lookup tables, right? And the data pass width is in the order of 256 bytes, 512 bytes and more. And that alone explains the increasing gap in performance between CPUs and switches. Because what we've been doing in switches has been to increase the data pass width in order to increase the throughput of switches. And the switches have been significantly tailored to handle data rather than the CPUs that have been tailored to handle instructions. And we are talking about data when we are thinking about the network today, right? If you can please move forward. Okay.
Is that the one?
Yeah.
Okay.
So a few years ago, we started a project that is called CAN, Computing as a Network, that is specifically tailored to handle this growing gap in performance by creating what we refer to as a tiny terabit data center, which pulls all the data center components into the computer. But having a computer where the network device is at the core of the computer, and all other components are what you'd think about as peripherals. So in the switches, we have limited memory resources. We don't have storage. We can't do all the operations that you can do in a CPU. And that's why you need more peripherals, such as the CPU and such as the CPU and the storage. And even if you are looking at in-network computing. Next slide, please. And what do I mean by in-network computing? In the context of this talk, when I'm talking about in-network computing, I'm talking about the execution of native host applications within the network using standard network devices. So I'm talking about NICs, I'm talking about switches. So for example, applications that we have already implemented within network devices are caching applications, so key value store, for example, consensus Paxos, for example, as well as all sorts of network functions, NAT, DNS, and so on. Next slide, please. The benefits that exist from using in-network computing start from the fact that every operation that you do within the network frees CPU cycles. So if you are thinking about the cloud, obviously freeing CPU cycles is important, but it also reduces the gap that we have in the performance between the CPU and the network. We can get from network devices a throughput in the order of billions of operations per second, while the latency of the computation is sub-microsecond. In terms of power consumption, you can get 3 orders of magnitude power efficiency, greater power efficiency by running within the network. That basically is equivalent to replacing several racks full of servers with a single network device. And that's work that I've presented just yesterday at UOSIS. And one additional benefit is that the cost of that is almost zero. It's almost zero, first of all, because you already have network devices within the network. But the other benefit is that you already pay for most of the power by moving the traffic through the switches. So you already have the packets coming through. You just underutilize the network as a resource. Next, please. So what I'd like to focus now is not on the in-network computing as much as, so what can we do with in-network computing? And I'd like to thank Eve for that, because she's actually prefetched for some of the upcoming slides, and these slides resonate with her talk. Can you please move to the next slide? So computing is becoming akin to infrastructure, even though it's not infrastructure today. And all sorts of infrastructure, whether that's electricity or sewage or traffic, it's all deployed at varying scale and for varying needs. So if you are thinking about junctions, then we have the mini roundabout and the roundabout and the bigger box junction, and then we've got simple interchanges and highly complex interchanges. In computing, we don't have all that, right? We only have the equivalent of mini roundabouts and roundabouts, which are the mobile devices and the servers, and then we have the data centers as the highly complex interchange. But we don't have anything in between. Can you please go back? Thank you. So if you're saying, yes, I've got racks full of servers, it's like saying, yes, I've got a junction with 40 mini roundabouts. No one wants to go through 40 mini roundabouts to cross a junction, which means that we need to have a better tailored computing infrastructure. Can you please move forward now? So this is the equivalent of what we have today. We either have the user going directly to the data center, or if you move to the next slide, then we've got edge computing in the middle. But we don't really have a hierarchy. So if we go to the next slide, we already have, in computing infrastructure by design, a hierarchy. Either if we are talking about different tiers within the network, either if we are talking about value-free routing, we have by design scalability here. So if you can move to the next slide, please. So why can we build computing infrastructure that is scalable? And by scalable, I refer to adding more levels of computing within the network, whether it's the edge compute that we have today, whether it's the higher performance aggregate compute, or maybe it's more local compute, like computing to the curb. Basically computing that is placed next to the user in the first location where you've got some communication infrastructure. So if you move to the next slide, please. So let's start thinking about having unified communication and computing infrastructure, where we have local compute nodes close to the edges, where we have edge compute, where we have aggregate compute. And this compute is switch-based computers providing in-network computing. And that's where it echoes back to the CAN project that I mentioned at the beginning. So as traffic comes from the user, we start doing the computation already, whether it's at the curb, whether it is at the edge, and whether it's closer to the data center. It may not apply to all applications, and I'm not touching in this presentation about all the potential applications, but we can gain a lot from using hierarchical computing and communication infrastructure. So if you can please move to the next slide. So some of the benefits here will be, first of all, terminating the data at the edge before it gets to the data center, which I believe most of you already agree with. It means that we can reduce the complexity at every stage. You don't need the same complexity at the edge as you need at the data center, and you don't need at the curb the same amount of complexity that you need at the edge. It will increase the scalability. And by scalability, I mean not just the scalability of the networking equipment, but the scalability when I think about handling the infrastructure over time and being able to sustain increasing data demands. It will also reduce power consumption. It is assumed that by 2025, about 20% of the world electricity requirement will go for data. So if we can half this amount by processing at the edge, processing closer to the user, reducing the entire amount of power that is wasted on the transmission of data, it's a significant gain. And it also provides better privacy and data control. And that will be the last part of my talk. So if you can move to the next slide, please. Okay, so one more slide before that.
Okay, because could you conclude soon, Noah?
Yes, I've got a couple more slides. So first of all, and I'll touch on this just briefly in this slide, cloud providers also have an incentive to move computing closer to the user from their perspective, whether it's for certain application and whether that's for reducing the load on the data center, increasing scalability. Next slide, please. But it also, and that's the more important part, it allows us to rethink the application deployment model. So today, if I'm a user and I'm using different applications, let's say that I have a Fitbit, the data from the Fitbit goes to the cloud, but I don't control in which cloud. In contrast, what I propose is a model where the users picks their compute service provider, and the compute service provider is the one that offers different applications. And it provides privacy as a service. It provides control over data as a service. If you can please move to the next slide, and I'll be going over these slides quite rapidly because they're supposed to be animation. The idea is to allow us to choose the provider the same way that we choose television service provider. So if you can move to the next slide, please. So if I go to a certain provider, they will offer me a set of applications, just like I have a set of TV channels today. And if I want more channels, it's the same as picking also to use Amazon or Netflix. So there are some more applications that may be in the cloud or in the next level of aggregation. If you can please move to the next slide. So the idea is to turn communication into also computing service provider that will allow us to choose our set of applications that are running within the network, which are running closer to the user, and provide us privacy and data control as a service. This will also increase the competition in the market and improve the resilience, because the failure of one cloud provider won't kill half of the internet. Can you please move forward? And it will also allow us to think about new types of computing models. So, for example, neighborhood clouds that may be led by the community rather than by companies. Next, please. And with that, I'm happy to answer questions.
Thank you so very much, Noah. Actually, for the sake of time, maybe we can combine the questions of this paper to an open discussion about what we wanted to do at the end, because I think this raises really, really good ideas about what network computing or computing in network will become. So I'd like to open the floor. And again, thank you so very much, Noah, and stay on because some of the questions you may be able better than us to answer. Thank you. Okay, you have a question?
Okay, so this is Hao Yusong from Huawei. I have a general question. I may misunderstood what's the real meaning of this compute in network. Actually, originally I thought this my thoughts actually close to what the last presenter actually showed. But to me, all the other use cases or applications seems to me is still use a network in the conventional way to provide the connectivities, or just working as a fabric. The actually application and the services are still happening at the edge devices. So I may like some clarifications what's the real meaning of this term and the scope of this research group. Thank you.
Can we return it back to you?
Yeah.
So I think, don't sit down. I will leave also even Jeffrey to barge in. I will return the question to you. What would you like it to be?
To me, my first thought is, you just do some forwarding related, or some doing some non-networking functions in network devices. That's my impression, but it seems for most talks today, I didn't get that sense.
Okay, maybe we saw them differently, but I think in principle we agree. If you look at the charter and if you look at the stuff we've been doing, basically it is what you are describing. And I think if you look at what Noah just presented, it also related to what you presented. And the industry network, the industrial network is also taking the applications and executing them closer to the user. So could you maybe clarify what your clarification means?
Yeah, maybe in that sense, maybe the term spin of the edge computing or some.
It is not just the edge.
Yeah.
I think Noah, and you can actually expand to this. I think Noah mentioned the issues of data centers and stuff, and we mentioned the continuum, and the continuum for us is very important. For example, Jeffrey is very interested in what is happening in the data center, and if you look at his draft, there's a lot of mentioning of consensus and key value. Obviously, there is a lot of stuff also happening at the edge, and this is what catches your imagination in some way. But I think what the important word in the presentation, and maybe we should put back the matrix picture, was this idea of a continuum. We do not want to limit it to the edge. We don't want to limit it to the data center. We don't want to limit it to something in between. We want actually to connect everything.
Okay, yeah, I expect to see more solid, tangible.
And please contribute your own comments. That would be great.
All right, thank you.
All right, Dirk Kutscher. So yeah, scoping is clearly the challenge here. So computing in the network, I mean, obviously there is a lot of computing in the network already. So, things like CDN, NFV, edge gateways, you can put application servers here and there. So we should be quite clear that this is not what probably this research group would be about, right? I mean, it's not just about arbitrary computing a network that already exists. It must be something a bit, say, advanced. And so with this continuum that you described, I think perhaps it's actually useful to also think about what could actually be out of scope, and maybe try to focus it a little bit coming from that angle. So secondly, I mean, this switch probability work that like Noah also presented, it's super interesting, and you can do many things. I'm a bit wary that we are inventing things like ISDN for network computing. So basically, a system where we say, oh, this reduces complexity a lot, and so we have a system where we can do value-added services in the network. So let's be really clear. I mean, okay, there are different research directions, of course, but I think what could be attractive is to think, so what does computing in a network have to do, say, with internet protocols and the way that internets work?
Yes, I mean, I think that's our unique position, which is that we live at typically layer 3, or, we kind of do some co-design with layer 2, but largely what kinds of protocols and ecosystem can the IETF bring to this discussion? That's the key question. But you're right, I think the scoping is absolutely important. And maybe we begin with the what's out of scope, and also maybe even cluster the topic areas and decide where we've got enough interest for people to be contributing ideas. So yeah, I think this is kind of an organizational, how and where to get started.
Yeah, I very much agree with that. Colin Perkins, relaying even from the Jabber room, there was a question from Pedro from NICT. He says that today we can choose the apps regardless of the provider, but with the shift in the model, we may be unable to choose an app that's not offered by our current provider, and if that's a step backwards, which I guess is a question about openness of the infrastructure and how to enable multi-use infrastructure.
Noah, do you want to reply to this? Is she still on? Yes.
I'm sorry, can you please repeat the question?
It was about the fact that right now we can actually choose applications that are not supported by our provider. And if we go to a model where, we have a set of applications that are, in a way, walled garden by the computing provider, that maybe it's a step backward. Do you have any comments on this?
Yeah, so the idea is, first of all, to focus on a subset of applications. So, for example, Facebook will never run at the edge. For Facebook, you will always need to run in the data center. But there is no reason that data for different IoT devices, from, for example, from my temperature control system or from my Fitbit will need to go to the cloud. And while only a certain number of applications may be supported, you can always go back to the model that you have today. You can always use whatever the application picks for you. You don't need necessarily to use the compute service provider. But as a person that really cares for his privacy, I really want to be able to choose which data center is guarding the data, or who is, what are the guarantees on privacy, on security, who is getting the data shared with. And even if we start with a limited number of applications and increase them over time, because it does require some changes to the applications as well, I already seen that benefits for the user that go beyond performance and have to do with the way that we handle our data, that we trust the data. And you may think also models such as data box. So data box is what I think about as the software complementary to this, to the CAN. So it is not supposed to apply to all applications that ever exist, but it is certainly the idea that it will apply to applications that matter to the users.
Thank you. Next question.
Oops.
And after the next question, we're going to close the line, please.
So Eric Nordmark, some thoughts in this space. So it's clearly a very large space, right? We talked about anything from sort of P4 up to, how does computing in the internet overall evolve with, Facebook versus running somewhere else for industrial applications. One thing that you might want to consider is saying, okay, what is actually new here? What is changing? And the sort of P4 angle that, well, we might be getting some different ways we can do some fairly limited compute. I'm not even sure I would use that term, but sort of saying, what does it mean to integrate this into a system where you use it and start from there and saying, how do I model this stuff? How can I think about the capabilities of the network? And while I do that, I sort of do the normal controller setting up the paths, the TSN support, whatever, time-sensitive networking. So I can actually think about what does an infrastructure look like that could do sort of things that the infrastructure can't do today, right? And then
Absolutely.
you can start pulling on that and saying, well, what else sort of it gathers around that, right?
Yes, and in fact, one of the notes here about next steps is about programmability. But if you could go back one slide we were trying to look for what's the commonality for orchestrating compute in the network. There are all these different facets to it. And so that was where we thought we would start. As you said, what's this kind of ecosystem that lives around it? One of the talks that we didn't get to present, which is one of the drafts, is about edge data discovery, or just the edge data problem. Like, who's working on that? How do you find or marshal that data? Where does it go? How do you name it? Bourdieu sort of gave a talk about that. So that's an area that we're not seeing any work going on in. So that was why we wrote a draft. But
yeah, and I think we're running out of time. Maybe you should ask your question really fast.
Yes. So Nicholas Fidel, building on what Eric said, one very interesting thing here is I think to try to understand the sort of the computational economics of this, because we're bridging between the networking and the compute, right? And there's a lot of, it's the same problem with edge, that you basically don't know, is it valuable in the bigger sense?
Yeah, and we have that somewhere in the charter, by the way. We're running out of time, as usual. So obviously, we're going to have much more activities. We'd like to push a lot of the discussions. We didn't have time to really go in depth on the list. We're going to also talk to the other, as we said, link with the other IETF and IRTF group that do the same thing. We're thinking of a potential virtual meeting, but we'll send that to the list again. And we plan to meet in Montreal when it's going to be great, because again, it's my hometown, and end of July is fantastic. So thank you so very much for coming. This, I think, is a great first meeting. We're very happy that we were accepted as a proposed RG, and it was because of the effort of a bunch of people in this room. You know who you are. Thank you very much. We survived. By the way, we're missing a blue sheet table. Okay, there was two.